Hi everyone, for the last talk of this third season for IGCP648 virtual seminar series. So it's the last talk for this season, but we'll come back in a couple of weeks, hopefully at the end of September with a new season. So new season, new battle, new great talk, etc. So just for those who do not know me, so I'm Luc, I'm your host today, and today we have Professor Andy Biggin, professor at the University of Liverpool in UK. He will present paleomagnetic field behavior over the last 2 billion years and its significance for Earth thermal evolution. Andy is the lead the University of Liverpool Geomagnetism Laboratory and the DEEP research group based there. His research focuses on describing and explaining the past behavior of Earth's magnetic field on timescale from centuries to billions of years. So Andy, the audience is all yours.
Thank you very much, Luc. Hi everyone, and yeah, I'd like to start by thanking the organisers, not only for inviting me to give this talk, but also just for laying on this great seminar series as well. I've really enjoyed tuning into the early events, and yeah, now it's my turn. So I'm going to be giving a fairly broad talk, reviewing lots of mostly other people's work. So big thanks to a whole bunch of people here. So large number of them at the University of Liverpool were mostly paleomagnetists, but there's also some numerical modelers in the team as well, and then some key collaborators as well. So Chris Davies, for example, is on the numerical dynamo simulation. Also Lee as well, who helped us get our samples for some of the results from Western Australia that I'll be showing later on in this talk. Okay, so start off with a big picture slide with two kind of very big picture images on there. So on the left here, you've got the the Earth cut in half, obviously, and this is the Burkean Earth, as it's termed by Trond Torsvik and co-workers. I should say that I'm not particularly, sort of nailing my colours to any particular model of how the mantle operates, but this was a good example to illustrate, I guess, the main points, which are not overly contentious, which is that slabs, when they're subducted, most of us agree that eventually they make it all the way down to the base of the mantle, where they will still be cool, and therefore they will suck heat from across the core mantle boundary and influence the flow that is going on in the liquid outer core beneath it. And then these in turn may interact with the thermal boundary layer down there, triggering plumes, which then some of which may rise all the way to the Earth's surface, causing large igneous prominences and hotspots and things like that. And in turn, those will be taking away hot regions from just above the core, and again influencing the outer core beneath. And then over on the right, I've got this conceptual figure that I was very pleased to see shown by the author in the plate tectonic battle that happened a little while ago in this seminar series. So I often show this figure myself, but I'm afraid that I tinker with it, and hopefully this won't upset the authors too much. But kind of we've got this no data available for the deep Earth in deep time. Well, I would posit that actually paleomagnetic data is the closest thing we've got to that. Now, obviously, paleomagnetic records come from geological units. But that said, if you trust the signal of the magnetic field that's recorded in these rocks, and some of these records are we think very trustworthy, then essentially it's mathematically very trivial to downward continue that signal to the core mantle boundary, and therefore to have kind of a pristine record of what's going on at a depth of nearly 2,900 kilometers, and that's going to tell you about what's going on in the liquid outer core, of course, where the main field is generated, but that's also influenced by the mantle sitting on top of it as well, as we'll discuss further. Okay, so I've got kind of a cheat sheet single slide here for convection in the outer core. I'm illustrating this with some flow diagrams taken from work by Julien Aubert and co-authors. This is showing the flow structure in the liquid outer core, a fairly sophisticated numerical simulation. And the key points for this is, well, first of all, the liquid outer core, the viscosity is extremely low. It's a dynamic viscosity similar to water, and we think that it's flowing at about the same rate as ocean currents, so millimeters per second, and it's expected to be highly turbulent. So what's driving all this flow? So it's convection, of course, but we're not sure to the extent at which that is thermal convection. We're not even sure if the core is superadiabatic, which is required to produce thermal convection. So in large part, we expect it presently to be driven by compositional convection. So it's fairly uncontroversial that the inner core is growing through time. The core as a whole is freezing from the bottom up. The iron in the alloy will preferentially freeze onto the surface of this growing inner core, and that leaves behind the lighter elements, whatever they are, and they can then form compositional plumes rising to the surface, positively buoyant because of their chemistry. Now, we don't get pure radial flow in the outer core because there's other forces at play here, as well as the buoyancy and the viscosity. So Earth's rotation in particular will be extremely important. Magnetic force may also play a lesser role as well. But what this rotation will tend to do is to organize this flow into helical columns that are aligned with the rotation axis. And essentially what that does is it subdivides the outer core into two regions, one which is inside a cylinder that you can imagine tangential to the inner core and aligned with the rotation axis, and then the rest of the core outside this. The really key point from this slide is this last point, which is the vigor of convection within the core is basically governed by the mantle to a large extent, is controlled by the mantle. And that's because this is all one big heat engine, and it requires heat to be lost to flow out of it in order to generate the work, and that all happens at the core mantle boundary. That's the only place that the core has to cool to, and given that the mantle is moves so much slower than the core, essentially the mantle imposes then a fixed heat flux pattern on the outer boundary of the outer core. And yeah, if the mantle cools down, then that's going to drive core convection faster, even though it's not thermal convection, and that's simply because if you cool the core faster, then the inner core can grow faster, and therefore you get more compositional convection. Now, obviously the inner core is growing, and if you play that back in time, at some point it will shrink to nothing, and you'll have an entirely molten core. And that point in Earth's history, when the inner core first nucleated, was a game changer for the geodynamo. And the reason being because you introduced then compositional convection. Before that time, you had you didn't have this rather efficient source of buoyancy in the outer core, and you're stuck with either pure thermal convection or perhaps some exotic other proposed mechanism of driving the dynamo, precession or exsolution of magnesium within the core or something like that. Okay, so having just said that the mantle plays a large part in controlling convection in the core, then we might expect to see signals of mantle convection in the paleomagnetic record, and we certainly do, or at least on those timescales we see strong variations. So the most obvious and famous of these is in the geomagnetic polarity timescale, so shown here on the left. So reversals occur in stochastic fashion. It's unpredictable when how long any individual chron is going to be, but you can see that there's an underlying tendency for reversal to happen, and that has changed over tens of millions of years. So crons on average were much longer in the early Paleogene than they are in the Neogene. And then if you go back into the mid-Cretaceous, then the magnetic field had stopped reversing altogether, and we're in a constant polarity superchron for around about 40 million years. Okay, and going back further than that, we have reversals again. This record here stops at 155, but deep toe magnetometer surveys and continental magnetostratigraphy strongly suggests that you actually had a hyperactive reversing field in the mid-Jurassic. So it was really reversing very strongly then. So this is the blue curve showing reversal frequency over this over the Mesozoic and peaking in the mid-Jurassic. And so a recent study that I was involved with, Jenny Kulikov and co-authors in JGR. This is, I think, kind of established, we hope, with some certainty that we do see variations in the dipole moment, in the average strength of the magnetic field that correspond to changes in this reversal frequency as well. So certainly if you look at the two extremes, this mid-Jurassic where the field was reversing very rapidly, the dipole moment was significantly lower than in the Cretaceous superchron. Okay, so that's what that says. A weak inverse relationship. It's not perfect so far as the data suggests. Should say all this noise as well that you might be, worried about. This is exactly what we'd expect from point recorders of the magnetic field. So most of these come from lavas, dikes, things like that. They're cooled very quickly, and the field changes quickly on short time scales. Okay, and all that which I've just shown, this inverse correlation, kind of fits with dynamo theory. So these are our I do apologize. So these are a bunch of numerical simulations that we're working with at Liverpool and Leeds, and so there are lots of different input parameters for dynamo simulations, and in these cases where we are where these points are connected by a single line, that's called single track, we're only varying one input parameter, and that is the Rayleigh number of the simulations. So what you see over here, we've got pure chemically forced dynamos, so just pure compositional convection. Here we've got thermally driven dynamos, and what we see is as you increase the Rayleigh number, you tend to go up on this axis. This is the proportion transitional axis. This is the proportion of time that these simulations are spending with their dipole more than 45 degrees misaligned with the rotation axis. So essentially time in which the magnetic field would be considered to be excursional or reversing. And what we see is as you increase the Rayleigh number in all these tracks, then nearly all of them, the tendency to reverse goes up, and quite sharply, because 0.1, if you consider 10,000 years for a reversal to take place, that's already at 10 reversals per million years, so a very high reversal frequency. Okay, and simultaneously, the true dipole moment, so the average strength of the magnetic field produced by the simulations, is going down. Okay, so we would expect an inverse relationship from these models between reversal frequency and dipole moment, and that is what we observe. More, what this is suggesting is that then this transition from a hyperactive field in the Jurassic to a superchron field in the Cretaceous is caused by a drop in the decrease in the Rayleigh number, in the forcing of the dynamo. And as I said, we'll expect that then to be governed by mantle convection, and the primary driver of mantle convection is subduction of the surface, so the negative buoyancy generated by slabs. So, we thought it'd be a good idea in this study that we published in 2018, Mark Hanslow, Matt Domeyer and myself, to have a look to see if it fits to first order, to look at variations in subduction flux and variations in the reversal frequency, given that we'd expect when the subduction flux is high, then that's driving mantle convection harder. We'd expect to be cooling the core more, and therefore to increase the Rayleigh number on the in the core and to drive more reversals. Okay, and this, but we also, so well we used then as our measure of subduction flux, we just looked at the area of subduction predicted by global plate tectonic model going back 400 million years. So this is Matthews et al. Model, and then we used a couple of proxies to verify how good this relationship was. So we've got the mantle component of the strontium flux ratio from Vandermeer et al. 2017, and we've got just a global compilation of detrital zircon ages as well. And what we found was all three of these records kind of showed variations on the, that were quite significant. So we've got, a factor of 3 change in the subduction flux on similar timescales to that which we were seeing these paleomagnetic variations. But we'd expect certain delays to be present in this, particularly the zircons, they arise from melting of the mantle wedge beneath the trenches. So, this was pushed back 15 million years to allow for that delay. But then, of course, you've got to get this thermal signature all the way from the surface down to the core mantle boundary. Okay, and what we did was then performed cross-correlation analysis to see what the optimum delay for that thermal transit time would be to produce then the best correlation. And we did manage to come up with a statistically significant correlation, allowing for 120 million years delay. So that's the thermal transit time. So then we do have to first order an explanation then for why the field should be varying on these sorts of timescales. And it's to do with ultimately, plate tectonics and supercontinent cycle governing the rate at which subducted material is entering the mantle. But I will highlight that this is a very, we were very happy that we were managed to find some correspondence here, but it's a very first order analysis. There's all sorts of things that could complicate this, not least being that the pattern, the spatial pattern at which the heat is sucked out of the outer core is likely to influence the magnetic field behavior as well. Okay, so I've talked about reversal frequency and dipole moment and the average strength of the field. Another aspect of paleomagnetic behavior that we can measure is something called paleosecular variation, so the directional variability of the fields. So I'll illustrate that through this study which we published last year. So this is the work of PhD student Yael Engbers at Liverpool, and we went to St. Helena in the South Atlantic, and we sampled a bunch of lava flows ranging in age from 8 to 12 million years ago. And this region today is very anomalous in the magnetic field, and it's been proposed by Tarduno and others that perhaps it is particularly prone as an area for anomalous behavior. So we tested that hypothesis by looking at the directional variability here. And we got these directions that are mostly shallow to the north, similar to today, shallow up. Some reverse directions, downward shallow to the south, and then some transitional directions in between. And what we do normally as paleomagnetists, of course, is to convert these to poles so that they're comparable with other sites where the direction might be quite different. So that's what we've done over here. And the average position of these poles is pretty close to the geographic pole, not quite on it. But the big story is not the average position, but rather the dispersion of these poles. So I put on for reference here this light blue present day field pole, which is quite anomalous by today's standards. So in most places around the world, you'll find a pole that agrees much more with a geographic pole, but it's quite anomalous in this particular area. But actually looking at a sort of geological perspective, we can see over this time period, it isn't so anomalous. We've got plenty of other poles that are similarly discrepant from the geographic pole. So we're able to sort of quantify that discrepancy a little bit better by comparing the properties of what we measured here with something, I guess, loosely termed as a paleomagnetic field, which is essentially the characteristics of the field when you average it over a few 100,000 years at least. And you can break this down into two aspects: the morphology and the variability. So in terms of the morphology, you've got the dipole moment and the average strength. You've got the dipolarity, the extent to which the dipole dominates, and then you've got the structure of what's left behind. In terms of the variability, you've got reversal rate, excursion rate, and then paleosecular variation, which can be intensity, or in this case, the variability in the directions. And we can quantify the angular dispersion given by a set of poles using this equation. And so this is just simply an angular standard deviation, but corrected for within site scatter as well. And then if we plot that then against a global compilation for the last 10 million years of lava flows that are recording VGP dispersion, then we see that this is significantly elevated above what we'd expect for the same latitude, sort of highlighting it as being highly anomalous. And just say this pattern then that we see quite a coherent pattern of increasing VGP dispersion with latitude over the rest of the globe, and that can be fit pretty well by a simple quadratic equation which we call model G from McFadden et al. 1988, whereby one parameter, this VGP A, defines the dispersion at the equator, and B defines the rate at which the dispersion increases with as you go away towards poles. Okay, and we can measure similar curves to this throughout geological history. Okay, so here are some records that were recently compiled from the Iceland workshops. So this is work by Dubrovin and a bunch of others. So from the Cretaceous superchron and from the period preceding the Cretaceous superchron, so the early Jurassic and the early Cretaceous and the Jurassic. And you can see these curves rather similar to each other, rather surprising outcome. Reversal frequency very different, paleosecular variation not really very different at all, quite similar. And then if you go back much further in time, so we've got Verkalainen et al. Looked over much longer time periods, gathered together these studies of these poles and estimated VGP dispersion, producing similar sort of curves for much earlier periods in Earth's history in the Precambrian. So this has always interested me because, yeah, one aspect of studying paleosecular variation is that it should relate in some way to the morphology of the field, and McFadden et al. Had their own ideas of how that might work, and we tested those original ideas with a bunch of dynamo simulations, and it didn't work at all. But we did manage to extract some useful information from them. So that's this power law here, which is published in this paper that came out late last year in Nature Comms. So we've got a nice power law between model GA parameter, so this equatorial VGP dispersion, which is something that we can measure, in rocks of Precambrian age, or compilations of rocks of Precambrian age, and then that's acting essentially as a reasonable proxy for this parameter over here, AD over an AD median, which is the average dominance of the axial dipole over the rest of the field. Okay, and so that is something that normally we require a full geomagnetic field model to estimate, right? And now we're able to come up with an estimate from it from something we can measure back into the Precambrian. So this is what the estimates come out as then of this axial dipole dominance for these different time regions. We've got the last 10 million years, then we've got the Mesozoic, and then we've got the Precambrian here, and they all overlap. Okay, very similar. So, and pretty large errors once you factor in the error on this power law as well. But this is still providing us useful information. It's saying that the field doesn't often look like this, very dipolar, and it doesn't often look like this, very non-dipolar. In fact, if you take the middle of this region into which these estimates fall, then you have something very similar to today's Earth field. Right? This is IGRF 2015 with AD over an AD median of about 10. Okay, so it looks like average axial dipole dominance has been surprisingly stable over geological time, but some caveats to that. So this work's submitted by a PhD student Ben Hanford at Liverpool, and he performed analyses like this back through the Triassic into the early Permian, and found that, yes, it was indistinguishable in that respect. It would just extend this time period. But then looking at the Kayman superchron, so the reverse superchron in the Permo-Carboniferous, that did look a bit more dipole dominated. Okay, I'm not sure it was statistically distinguishable, but it definitely looked at the top end of this. And I have to put this in because I understand there's a number of paleomagnetists here. I've got to say, when I'm talking here about axial dipole dominance, that's at the instantaneous field. That is not the same as saying whether the field is GAD-like or not when you average it over a large amount of time. So this plot is looking at a measure of how GAD-like the field is, so using the inclination anomaly. So the extent to which your expected inclination from GAD is discrepant from that which you observe at the latitude. Okay, and here the models do not show quite such a strong correlation, but it is statistically significant. Now, more reassuring, we know both of these things for the last 10 million years, and that's plotted here as this purple point, and that falls right bang on this trend. So that's quite reassuring. And then if we look at the model GA parameter for those 4 periods that I showed you before, you can see that they would translate to inclination anomalies that are similar to the last 10 million years. So that's peaking at about 7 degrees inclination anomaly, which isn't great, but that's an extreme. Most latitudes inclination anomaly doesn't exceed 2 or 3 in the last 10 million years. Okay, so I did promise to talk something on thermal evolution. So this is a paper that is it's only got minor corrections to do for GGI, so expect it to be accepted quite soon. So this is looking at a bunch of different thermal evolution models and seeing what their implications, what they predict for the dipole moment evolution through time. Okay, so what we've got is 2 models here, one showed by the dashed line, one showed by the continuous line, and the black is showing the total heat flow across the core mantle boundary. So we have some idea of what it is, but pretty vague today. No idea what it was in the past. It depends on how hot the core was. So we've got 2 models here that go in very different evolutions. And what you can see then is, and red is the power available to drive the dynamo. Okay, so how efficiently it can use this heat flow across the core mantle boundary to drive to generate a magnetic field. Okay, and you can see that this track through large parts of geological history, these track fall somewhat underneath the total heat flow. Okay, but then suddenly there's a massive non-stationary and these powers jump up, and that is the point of inner core nucleation. Okay, because suddenly you're introducing this game-changing efficient process of compositional convection within Earth's core, so that suddenly produces then a much it gives the dynamo much more power to generate a magnetic field. And then the big thing that was done in this systematic study was to scale that available power to what we'd expect the dipole moment to be, which is, of course, what we can measure going back through time. And here are the predictions of 3 different models. And as you can see, in these cases, there's a slight decline up to the point of inner core nucleation, and then there's a very sharp rise. Okay, so the weakest point is just before inner core nucleation, and then a very rapid rise, and then it does something. It doesn't do much after that point. Okay, so here we've got dipole moments, binned, large bins here for comparison, but what you can see, problem is we've got these red points in this critical time period. Red in this plot means that fewer than 10 data points available, so really largely unconstrained in these time periods. But we've nevertheless, as paleomagnetists, tried to make predictions of when the inner core did nucleate based on dipole moment data before. So this was our study from 2015, when we suggested that this point of nucleation happened sometime in the Mesoproterozoic between 1 and 1.5 billion years ago, and on the basis of a distinct distribution of dipole moments that's much higher after this time period, okay, in this later bin. Okay, now this manuscript, this paper has received a lot of attention, and some of that has been deleterious in the fact that we've gone and looked at these results in particular from the Garda lavas in southwest Greenland, and showed those to be somewhat questionable. Okay, so you lose these, and obviously the case becomes harder to make that you did have a jump across this time period. And a counter hypothesis was proposed by Richard Bono and co-authors in 2019. So they measured extremely weak paleointensities from the Sept-Îles intrusion in Quebec, and proposed that that was a point just before the inner core nucleated, and showed this, this thermal evolution model cutting through time averaged data here, and implying that inner core nucleation just happened some point soon afterwards. Okay, so this is obviously a very big, important field for paleomagnetism. So we devoted a lot of our effort at Liverpool to try and fill in more data around these time periods. So I'm going to show you some of those now. So here we're zooming in on the Ediacaran. And so the time period 480 to 620, so into the Phanerozoic as well. I'll just point out the y-axis here only goes up to 3.5 times 10 to the 22 meters squared. That's less than half of the present day dipole moment, which is 7.8. So this is truncated at very low values. Okay, and here's Sept-Îles there, this very low value. And since then, I should say this is largely the PhD of Dan Thalner has been contributing to this, with collaborators in Russia and Ukraine. We published these paleointensities from the East European craton traps, and these overlapped in age with Sept-Îles and confirmed, indeed the field was extremely weak around this time. And then Dan also worked on these Grenville dikes from southeast Canada, and here slightly older, obtained these really super weak paleointensities, and this one's the weakest of the lot. And just for reference, point out the actual paleointensity, which is less than 2 microtesla. That's less than what has been observed by the InSight lander on the surface of Mars. So we're really at the detection limit here of how low we can expect, paleointensities of an active dynamo to be. And then most recently, a paper that we hope will be accepted very soon in JGR, the Skinner Cove lavas from Newfoundland. And here some low values and some higher ones. And that was interesting because these are a little bit younger than the rest. And put all that together, and you look at the extant data from Malawi and from the Urals, and it looks kind of quite intriguing, as you've actually got a sharp rise here, as we might expect from inner core nucleation. So that's all nice, but yeah, things become a bit more complicated when you add more data to the mix of different ages. So now I'm talking about the work of PhD student Simon Lloyd, and so 2 papers here, one in GGI this year, so from the Franklin dikes in the Canadian Arctic, so 720 million years old, and these gave weak paleointensities. Okay, and these sit quite nice on this dashed line here, which is the thermal model that I showed you from Bono et al. So that all looked good. But then we went to Western Australia with Lee, and we sampled the Mundine Whelks and the Wells dikes and the Bangamole sills. And these were tricky to get any data from, but we did manage to get some. And this is a paper that's submitted to G-Cubed. And the Bangamole ones, they showed low data, nearly the same age as the mid-continent rift, which show all these high paleointensities. But these showed, somewhat lower and more in keeping with this trend. So this all looked kind of promising. But then we've got the Bangamole sills as well, which are nearly, which are only 30 million years older than the Franklin dikes, and these are giving, high near present day dipole moments estimates. So, what this is suggesting really is that you've got, field variations happening on tens of millions of years in the Precambrian, and there's no reason not expect that, because that's what we see in the Phanerozoic as well. But it does mean that it's going to make it harder to delineate a trend like this. Okay, then going to later time periods, I'll highlight the work of Louise Hawkins at Liverpool. And so she gathered a load of data from the mid-Paleozoic, so from early Carboniferous and Devonian age rocks, and she also assessed the quality of the paleointensity from across this time period and through the later Paleozoic. And this is a key figure from a paper that's in press at PNAS at the moment, that's introducing this idea of a mid-Paleozoic dipole low. So to put this in, so we've got this period, this interval here where the field was again very low. So I'm sorry I keep on flipping the time axis on you, by the way, but it's just the way these things are presented. But yeah, so we're just off here. So 500, the Ediacaran is just back here. Got very little data between then and the Devonian, the mid-Paleozoic. So we don't really know what's going on here. We think there was a superchron in the Ordovician, so that might suggest that the field got strong, but then it collapsed again in the mid-Devonian. Okay, so the field did not undergo a monotonic increase, to these high values. It fell down, it collapsed again weak. So once more, we're thinking this is this mantle forced variations rather than suggesting that this might actually be the real inner core nucleation age. Okay, so this is just flipping the time axis on you again, just a summary of the new data presented. This in yellow, new data from Liverpool and with our collaborators for the last 5 years. And yeah, so highlighting two periods really, where we think the field, might have been non-uniformitarian. So we've got this mid-Paleozoic dipole low that I've just been talking about, and then this Ediacaran, which is even weaker, of course. And we don't really know what secular variation was doing in this time period. We don't even know what reversal frequency was doing this time period. We've tried, especially in the Devonian, we've tried to get magnetostratigraphy out there, but we've really struggled. Okay, but I guess the key question that we need to try and address here is whether the Ediacaran then is really this, is certainly weak, but was it weak because the field was, the dynamo was, at death's door, and it could, it was just about to die out, and it needed the inner core to rejuvenate it, or was it a cycle like we see in the mid-Paleozoic or in the Jurassic even, which we think is actually a result of it being very strongly driven by mantle convection and pushing it into this more multipolar state, which has a lower dipole moment associated with it. So these are the sorts of questions we need to ask, and it's dynamo models that are going to help us answer these sorts of questions. And yeah, so I've got a few slides here, but I'm going to zip through them really quickly because I'm nearly out of time here, and the details are not relevant. You can look at the papers if you're interested in more. But essentially, when we started using dynamo simulations, we were shocked at how non-Earth-like most of them were. So we developed a set of criteria to test this Earth-likeness. And the original batch of 46 simulations that we got, most of which were sold to us as being Earth-like, failed most of these criteria that are based on properties of the magnetic field, paleomagnetic field from the last 10 million years. So we've got kind of two scores here. QPM score is how many of these 5 criteria they meet, and none of them met more than 3 simultaneously. And then we've got QPM misfit score, which is you sum up these normalized errors based on the uncertainties between the observations and or between the models and the expected values from the paleomagnetic records, and they should sum to less than 5. And we didn't get any that summed less than 5. But here's an example of one which did pass at least our 2 paleosecular variation criteria. Okay, and I'll skip over that and just go to this slide, which is saying, but then, we kind of got a bit smart with this, a bit more systematic, and learned how to tweak existing models to try and make them fit these criteria better. And we have come up with more than one model, but I'm showing one here, which has a very low QPM misfit of less than 3. and it satisfies 4 but not 5 of the 5 criteria. The one it fails is the reversal criteria. So we can see there's a time series of it running for 4.5 million years, and there's several excursions. There's a reversal in there, but that's not very much compared to the last 10 million years. So it doesn't quite reverse enough, but in every other respect, paleosecular variation and inclination anomaly, it does seem to look like the Earth. So this is, you know, a simulation that we can now say represents, you know, is a fairly good representation of the Earth of the last 10 million years, and then we can perturb that and see what happens to the magnetic behavior. So to give you an example of this, we increase the Rayleigh number not by very much, from 1.6 times 10 to the 7 to 1.8 times 10 to the 7. Everything else is the same, and suddenly we flip the magnetic behavior quite dramatically. So it reverses a lot more, and it enters sometimes this kind of hyperactive state where basically the dynamo just collapses altogether. So this is suggesting, yeah, you don't need strong changes in the forcing to get the paleomagnetic field to change its behavior. And so, you know, by looking at these in a bit more detail, we can hopefully solve some of these questions. So this is my summary. Hopefully I've convinced you that paleomagnetic field behavior, particularly if you integrate it with numerical dynamo simulations, then, you know, they have the potential to give us a lot of information about the deep Earth in deep time. And yeah, so what we've seen so far is that some aspects of paleomagnetic field behavior varies strongly on mantle convection timescales, tens to hundreds of millions of years. So we think that's likely caused by variable mantle forcing. But interestingly, paleosecular variation and the linked morphology, so the axial dipole dominance, does not seem to vary quite so strongly. That's good news for paleomagnetists doing paleogeography studies, of course, because it means that GAD is still, you know, reasonably good through most of geological time. But yeah, we're certainly not ruling out that there were certain time intervals, including the Ediacaran and the mid-Paleozoic, which might have been non-uniformitarian in their shape as well. And for now, you know, we desperately need more data, and that will yield better insight. But for now, it's difficult to infer the date of inner-core nucleation from the paleomagnetic trends, I believe. So that's it. Thank you for listening.
Thank you, Andy.